Now problem set 2.6 is solution to 2.92. We'll be dealing with a circular right cylinder and how it is prevented from rolling due to a string attached to its center. That we'll discuss by taking moment of different forces about different points. So let us begin. A smooth right circular cylinder. This is the original diagram. This is a circular cylinder. Its radius is r, and the cylinder, it rests on a horizontal plane. Means there is the plane is horizontal and kept from rolling by an inclined string AC. The string AC stops it from rolling to the right hand side, and why it should roll I will explain. By an inclined string AC of length 2r. The length of the string from A to C, which is a string, so there will be a tension in it. The length is 2r. A prismatic bar AB. This prismatic bar AB of length 3r. The length of the bar is 3r, and weight Q is hinged at point A. This prismatic bar has a weight Q and leans against the roller as shown. Find the tension S that will be induced in the string AC. Now, so let us discuss. AC is a string, so the force is a tension force S. If you consider point C, the tension force will be away from point C. If you consider point A, it will be away from point A. The same S. And the length of the prismatic bar AB is given. It has a weight. And the length of the string AC is also given. From here to here is 3r. Now, two questions they arise in your mind. Why the cylinder should roll? Now, since the prismatic bar has a weight, if you keep the cylinder here on the horizontal surface and the prismatic bar is inclined towards it, means a part of its weight will be used to roll this circular cylinder towards right. But there is a string attached. So the tension in the string S can hold it back. So we'll find how much is that, how much is the tension developed in the string from holding the cylinder back from rolling towards the right. Now, what prevents it from rolling is the tension in the string. Let me once again explain. This prismatic bar has a weight W. So, since it is tilted like this, so it will apply some force on the circular cylinder, due to which it will start rolling to this side. And the string, due to the tension S, will hold it back. Now, I have redrawn the diagram for you again. Now, now look. This is the point of contact of the cylinder with the horizontal surface. AC is the string. The tension is S, acting from away from point C. If you consider C, acting from point away from point A, acting away from point A, if you like this. And this is the midpoint of the prismatic bar. The weight is acting vertically downward. That is Q. Value of Q is not given, so S will be found out in terms of Q. And this is the point of contact, and the prismatic bar here will apply some action force to this side. Let it be RE. So at the point of contact, the circular cylinder will apply the same reaction force, RE. So these are the action-reaction pair, RE. This RE pointing from this side to this side is acting on the cylinder. This RE pointing from this point to this side is acting on the prismatic bar. That is to be understood. Action reaction, they act on different bodies. So now D is the midpoint of AB. D is the midpoint of AB. Now, since the length of AB is given, so from A to D will be equal to from D to B. So from A to D will be equal to D to B, that will be 3r by 2, because the length of AB is 3r, that is 1.5r. Now triangles AEC. Now look at triangle AEC and triangle AFC. AFC. This is 90 degree here. This is 90 degree here. So AC is the common hypotenuse, which I have redrawn it here. These two triangles are similar because these two angles are 90. This is the hypotenuse. And there is a theorem called RHS, right hypotenuse side. Right hypotenuse side. This is right angle, hypotenuse. And which side is same? From E to C is equal to from C to F. That is equal to radius of the cylinder. So under these three conditions, the two triangles are similar. Therefore, the angle EAC will be equal to angle FAC is equal to alpha C. And this length from here to here is given as 2R. That is the length of the string. And the tension is like this. Right. Now, then let us take sine alpha to find out alpha. So sine of alpha will be perpendicular over hypotenuse, that is CE over AC, that is equal to R over 2R, that is 1 over 2. So alpha comes out to be 30 degree. So alpha comes out to be 30 degree. There is again a diagram redrawn for you for better understanding. Look at here. This is the prismatic bar here. This point is E, where this RE is the reaction. This RE acting on the prismatic bar at point E is the reaction force applied by the cylinder on the prismatic bar. And since alpha is found out, this angle is alpha. That is same thing as this angle is alpha, which we found out as 30 degree. So I have shown it here. From the midpoint, Q is acting vertically downward. This is your tension force acting away from point A. And whatever will be the reaction force here at A, I have resolved into rectangular components. Reaction at A along y-axis, reaction at A along x-axis. I will be considering moment of the forces about this point. So this will not contribute any moment about this point. This will also not contribute about any moment about this point, because both of them are passing through the same point, means they don't have any perpendicular distance. Now I have again redrawn. Now D is the midpoint of the prismatic bar AB. So from A to D will be half of AB, that we calculated as 1.5 bar. From this point is acting your weight of the prismatic bar Q vertically downward. At this point is G. So, and at this point RE is to this side. Sorry, at this, not RE is to this side. So about point A, RE will have a turning effect, that will be RE times this length, AE. Now similarly, about this point, the weight Q will have a turning effect, Q times this length, AG. Now let us take the moment about point A. Now, so we need to find out AE and AG also. So RE times AE will be equal to Q times AZ. RE times AE about point A will produce an anti-clockwise turning effect. Q times this perpendicular distance AC will provide a clockwise moment about point A. Since it is in equilibrium, so RE times AU will be equal to Q times AZ. Make it as equation 1. But we need to find out AE and AZ by applying sine cos functions to different right angle triangles. Now look at triangle AEC. AEC EC, 90 degree at E, and this angle is alpha. So if you take cos alpha, it will be base over hypotenuse. It will be AE times AC. AE times AC, so cross multiplying, we get AE is equal to AC times cos alpha. AC, the length of the string is given as 2, or 2 times cos 30, because alpha is 30. So we'll put this value of AE in equation of 1. Then look at triangle AGD. AGD, right angled here. Now, and angle at A, that is angle DAG. This angle is 2 alpha. So cos of 2 alpha will be base over hypotenuse, AG over AD. AG over AD. So if you cross multiply, you get AG is equal to AD times cos 2 alpha. AD is found out because it is D is the midpoint, so it is 1.5 power. Alpha is 30 degrees, so cos times 2 into 30, cos 60. So this is the value of AZ. Now put these two values in equation 1. Then it becomes simple. So I have put the values in equation 1 to get RE multiplied by 2, or cos 30 is Q times 1.5 power cos 60. Keep RE on one side. This R multiplied, that cancels. So 2 times cos 30 goes to the right hand side, comes to the denominator. So R cancels here. I can cancel here. I didn't cancel it here. I am cancelling here. Now put the value of cos 60, cos 30. So we get RE, the reaction force, action reaction force at RE is equal to 0.43301 times the weight of the prismatic bar, that is Q. Now we have to again apply the principle of moments to the point F. So now is interesting. Now look, if you consider the tension force is in the string AC and consider the point C, it is to this side. So one component of S will be to this side, another component of S will be to this side. Now this will be alpha. So this will be your S cos alpha, this will be your S sin alpha. Similarly, this action force RE applied by the prismatic bar on the circular cylinder, if you shift this RE to this point, RE will be pointing to this side. So this will also have two rectangular components, one to this side and one to this side. Now that I am showing here in a different diagram here at point C. So this is your S, this is your alpha. Now why this is alpha? Look, this line is horizontal, this line is horizontal, this is found out as alpha, this is the transversal. Since this is alpha, therefore this is also, this angle is alpha. So that is what I have shown here. Since this is alpha, so this is your S cos alpha, this is your S sin alpha. So this action force RE applied by the prismatic bar at point E on the cylinder is to this side, RE. So let us split RE into two components. This is your RE. So this will be one component of RE, this will be another component of RE. Now the question is, which angle is 2 alpha? Now this line is horizontal to this. So I have shown it in a different diagram here. Now look at here. This is your RE, this is your 2 alpha. So one component of RE will be to this side, will be RE times sine 2 alpha, and to this side will be RE times cos 2 alpha. And component of S to this side will be S cos alpha, to this side will be S sin alpha. And that is what is shown here. Now we'll consider the moment of the forces about point F. Now the component of S, that is S sine alpha, passes through the point F, and the component of Re, that is Re cos 2 alpha, also passes through the same point F. Means these two forces, they do not have a perpendicular distance from the point F. So these two will not produce a turning effect. So the turning effect, but this S cos alpha from the point F has this perpendicular distance, and this Re sin 2 alpha from this point also has the same perpendicular distance. So let us take the moment of these two forces about point F. Now, so that is what I have said. Now split S into two rectangular components, S cos alpha, S sin alpha are to C, and split Re into two rectangular components, Re cos 2 alpha, Re sin 2 alpha are to C. And as you can see, well, imagine from the diagram, Re cos 2 alpha and S sin alpha, both of them pass through the same point F. Re cos 2 alpha, S sin alpha, they pass through the point. Both of them don't have any perpendicular distance from F. So the turning effect of this as well as this about point F is 0. Only we are left with these two forces, which will have, one will have a clockwise moment, the other will have an anti-clockwise moment. So let us take the moment about point F. Re cos 2 alpha and S sin alpha pass through F, so both don't produce any turning effect about point F. Therefore, sum of the moments about point F is equal to 0. Since it is in equilibrium, it is stopped from rolling. So S cos alpha times R is Re sin 2 alpha times R cancels. So S becomes Re sin 2 alpha over cos alpha. Re we just calculated is equal to 0.43301 times the weight of the prismatic bar, that is Q. So put the value of Re, put the value of alpha 30, this comes out to be 0.43301 times the weight of the prismatic bar. So that is the tension developed in the string, which stops the cylinder from rolling. So that's all about. It's a good numerical problem. It was asked once in JEE Advanced probably. I think the videos are interesting for you. If you like, feel free to subscribe and pass on to your friends studying engineering mechanics in different engineering colleges, either in civil engineering or in mechanical engineering, or in some colleges. This is also a part of the course curriculum in computer science also. So please pass on to them. Thank you.